Tonight, we're going to explore a genuine scientific mystery, and it is hiding in the most familiar place imaginable, inside the sun. For decades, scientists believed they understood our star better than almost any other object in the entire universe. They had measured its size, its temperature, its age, its mass, the way its light is made. They had built detailed models of its hidden interior, all the way down to the nuclear furnace at its core. And those models worked. They matched the measurements with breathtaking precision. The sun, scientists declared, was essentially solved. We understood it. The textbook was closed. Then they found a way to look inside it, not with a telescope because a telescope only sees the surface. They found two almost impossible ways to peer straight through the blinding outer layers and read the conditions deep within, in the core itself. And when they did, when they finally checked their perfect models against the real, measured interior of the sun, something was wrong. The inside of the sun, it turned out, does not add up. The structure we measure does not match the structure our models predict. There is a discrepancy buried in the heart of our star that, by everything we thought we knew, simply should not be there. And after years of work by some of the best scientists on Earth, no one has been able to fully explain it. By the end of tonight, you're going to understand exactly what scientists detected inside the sun, why it broke a model that had worked perfectly for decades, and what the strangest proposed explanations might mean, including the possibility that something invisible is hiding in the core of our own star. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why this discovery matters so much, you first have to understand how confident we were, because the sun was not just any star. It was the star, the one we were sure about. Out of all the hundreds of billions of stars in our galaxy, every single one except our sun is impossibly far away, reduced by distance to a faint point of light. We cannot visit them. We cannot study their interiors in detail. Everything we know about how stars work, how they are born, how they burn, how they age and die, rests almost entirely on our understanding of one single example: our sun. It is the benchmark, the calibration point, the one star close enough to measure in extraordinary detail. And from it, we built our entire theory of how all stars work. And for a long time, that theory was a triumph. Scientists constructed what is called the Standard Solar Model, a detailed mathematical description of the sun from its core to its surface. The model takes everything we know: the sun's mass, its age, the way nuclear fusion behaves, the way energy flows through its layers, the mix of chemical elements it is made of, and from all of that it calculates exactly what the inside of the sun should be like, how hot it should be at every depth, how dense, how fast sound should travel through it, where the boundaries between its internal layers should sit. For years, every time scientists found a new way to test that model against reality, it passed. The predictions matched the measurements with an accuracy that was, frankly, astonishing. To a fraction of a percent, the model and the real sun agreed. It became one of the great success stories of modern astrophysics. We had taken the most important object in our existence, and it seemed fully understood it, all the way down to its blazing core. There was a quiet confidence in the field. The sun was a solved problem. And that confidence is exactly what makes the rest of this story so unsettling. Because confidence like that is fragile. It holds only as long as every test keeps passing. And the moment scientists developed a genuinely new way to look inside the sun, a way to check the model not against the surface, but against the actual measured interior, that confidence began to crack. The sun had been hiding something, And to find it, scientists first had to solve a problem that sounds completely impossible. How do you see inside a star? Here is the obstacle that should make this entire story impossible. You cannot look inside the sun, not in any direct way. And once you really think about why, it becomes genuinely baffling that we know anything about its interior at all. Start with the basic problem. The sun is opaque. When you look at it, you are seeing only the photosphere, the thin outer layer where the plasma finally becomes transparent and lets light escape. Everything below that layer is hidden. The light that reaches your eye comes from the surface, and the surface alone. You cannot see through it any more than you can see through a wall of fire. Below that glowing skin lies hundreds of thousands of miles of dense, churning, blindingly hot plasma, and not a single photon from the deep interior ever travels straight out to be seen. The inside of the sun is sealed behind an impenetrable barrier of its own light, and it is not as if we could ever go there and look. The sun is 93 million miles away, and even if we could somehow cross that distance, anything that approached would be vaporized long before it arrived. There is no probe that could survive a plunge into the sun. There is no drill that could bore into it. The core sits beneath an unimaginable weight of superheated matter at temperatures of millions of degrees and pressures beyond anything we can create. It is, physically, one of the most inaccessible places in the entire universe, closer to us than any other star, and yet more sealed off than almost anywhere we can imagine. So think about what that means for science. The interior of the sun, the core where all its energy is made, the layers through which that energy flows should be completely unknowable. A perfect black box. We can see the outside. We can measure the light and heat that escape. But the actual conditions inside, the temperature at the center, the way the layers are arranged, the speed at which the core spins, all of that should be forever beyond our reach, locked away behind that wall of fire. And yet we know these things. We have measured them. We have maps of the sun's interior so detailed that scientists can argue over discrepancies of a fraction of a percent. We know roughly how hot the core is. We know where the internal layers meet. We know how the inside rotates. All of it from the outside without ever touching the interior. It seems impossible. And the only reason it is possible at all is that the sun, it turns out, gives off two things that can carry information straight out of its hidden depths and into our instruments. One is a kind of sound, the other is a ghost, and together they are the only eyes we will ever have inside a star. But before we use them, we need to know what we are actually looking for. We need a map of what is supposed to be down there. Before we go hunting for what shouldn't be inside the sun, we need to understand what is supposed to be inside it, because the sun is not a uniform ball of glowing gas. It has a structure, a series of distinct layers, each one doing a different job, each one with its own conditions. This hidden architecture is what scientists spent decades mapping, and it is where our mystery is buried. At the very center sits the core. This is the engine, the only place in the entire sun where nuclear fusion actually happens. It makes up a relatively small fraction of the sun's total size, but it is where all the energy comes from. The conditions here are almost beyond comprehension. The temperature reaches around 15 million degrees, and the pressure is so immense that hydrogen is crushed and fused into helium, releasing the energy that will eventually become sunlight. Everything the sun does, all its light and heat, begins in this core. Wrapped around the core is the next layer, called the radiative zone, and this is a strange and important place. The energy made in the core has to get out, and in the radiative zone, it travels in the form of light, as photons. But it does not travel in a straight line. The radiative zone is so dense that a photon can only move a tiny distance before it slams into a particle and is absorbed and re-emitted in a random direction. So the energy bounces and ricochets its way outward, painfully slowly, taking an enormous span of time to cross this single layer. How easily that energy flows through the radiative zone depends critically on what the layer is made of, and that detail is going to matter enormously later. Then, at a specific depth, something changes. The plasma can no longer carry the energy outward by radiation alone, and instead it starts to physically churn and boil, like water in a heated pot. This outer layer is called the convective zone, and here great columns of hot plasma rise toward the surface, release their heat, and sink back down. The boundary where the radiative zone ends and this churning convective zone begins is a crucial marker, sitting at a very particular depth inside the Sun. Remember that boundary. Its exact location is one of the most important clues in this entire mystery. And right at that boundary lies a thin, mysterious transition layer called the tachocline, a region of intense shearing where the deep interior and the outer layers rotate differently. It is thought to be where the Sun's powerful magnetic field is generated, and it is one of the least understood places in the entire star. So that is the architecture: a fusion core, a slow radiative zone, a churning convective zone, and the boundaries between them, all at specific, predictable depths. The standard solar model tells us exactly where each of these layers should sit. Now all we need is a way to check whether the real Sun agrees. And astonishingly, the Sun itself gives us the tool, in the form of sound. Here is the first of the two impossible windows into the Sun's interior, and it is genuinely one of the most elegant ideas in all of science. We cannot see inside the Sun, but we can listen to it, because the Sun is ringing constantly like an enormous bell. The churning, boiling motion of the plasma near the Sun's surface generates sound waves, pressure waves that travel downward into the body of the star. And these waves do not simply fade away. They travel through the interior, bend and refract as they pass through layers of different density, bounce off the inner structure, and travel back up to the surface, causing the entire face of the Sun to gently vibrate, to pulse up and down in a vastly complex pattern. The whole Sun is humming with sound trapped inside it, oscillating in millions of different ways at once. Now here is the key. The way those sound waves travel, and the way they make the surface ripple, depends entirely on what they pass through on their journey. A sound wave that travels deep through the hot, dense core behaves differently from one that only skims the outer layers. The speed of sound at every depth, the location of every boundary between layers, the temperature and density throughout the interior, all of it leaves its fingerprint on the pattern of vibrations we can see on the surface. So by measuring those surface oscillations with extraordinary precision, scientists can work backward and reconstruct the conditions deep inside the Sun, layer by layer, all the way down toward the core. This field is called heliosismology, and it works just like the way geologists study the inside of the Earth. When an earthquake sends seismic waves through our planet, scientists measure how those waves arrive at different points on the surface and use them to map the Earth's hidden interior, its crust, its mantle, its core, even though no one has ever drilled more than a tiny fraction of the way down. Heliosismology does exactly the same thing for the Sun. The Sun's own sound waves become a way to see straight through the wall of fire and map the structure within, and it works spectacularly well. Using heliosismology, scientists have measured the inside of the Sun with stunning accuracy. They have pinned down the speed of sound throughout the interior, They have located the exact depth of that crucial boundary where the radiative zone meets the convective zone. They have even measured how much helium the sun contains and how its different layers rotate. For the first time, we had a real measured map of the sun's interior, not a prediction but an observation. And for a while, that measured map agreed beautifully with the standard solar model. The two matched. It was a triumph. But sound is only one of our two windows. The other comes from the core itself, in the form of a particle so strange it can fly straight out of the center of the sun without slowing down. Sound lets us map the structure of the sun's interior. But there is a second window, and this one looks straight into the very heart of the star, into the core itself, at the fusion reactions happening right now. It comes in the form of a particle called the neutrino. Neutrinos are produced by the nuclear fusion in the sun's core. Every time hydrogen fuses into helium, neutrinos are released, vast numbers of them, streaming outward. And neutrinos are among the strangest particles in all of physics because they almost never interact with anything. Remember how a photon of light, made in the core, takes an enormous span of time to bounce its way out through the dense interior. A neutrino does not bounce at all. It passes through the entire bulk of the sun, all that crushing, superheated plasma, as if it were not even there, escaping the core in about 2 seconds and flying straight out into space. Then it crosses to the Earth in about 8 minutes. Think about what that gives us. A neutrino arriving at Earth carries direct, fresh information from the core of the sun, from the exact place where the energy is made. The light we see left the surface, but it was generated in the core tens of thousands of years ago and has been crawling out ever since. A neutrino, by contrast, tells us what the core is doing almost right now. It is the most direct messenger we will ever receive from the center of our star. By counting the neutrinos arriving from the sun, scientists can effectively measure the rate of fusion in the core, and from that, the temperature and conditions at the very center. There is just one problem. Because neutrinos interact so rarely with matter, they are extraordinarily difficult to catch. Out of the trillions upon trillions that pass through the Earth, and through your own body, every second, only the tiniest handful will ever interact with anything in a way we can detect. So to catch even a few solar neutrinos, scientists have to build enormous detectors, great tanks filled with thousands of tons of fluid, buried deep underground in mines, shielded from everything else, and then wait patiently for the rare flashes that signal a neutrino has been captured. And so, by the late 20th century, scientists had two independent, almost magical windows into the inside of the sun. Sound waves, mapping the structure of its layers, and neutrinos reporting directly from the fusion in its core. Two completely different methods, probing two different aspects of the hidden interior. If the standard solar model was correct, both windows should confirm it. The structure measured by sound should match the predictions. The neutrinos counted from the core should match the expected number. Everything should line up. But when scientists finally counted those neutrinos arriving from the sun, they got the shock of their lives. Because most of them were missing. When scientists built their first great underground detectors and began counting the neutrinos streaming out of the sun's core, they expected to confirm their model. They knew how much fusion should be happening in the core. They knew how many neutrinos that fusion should produce. And so they knew, in advance, roughly how many they ought to detect. The experiment was supposed to be a confirmation, a final tick of approval for a model everyone already trusted. Instead, the detectors found only about a third of the expected neutrinos. 2/3 of them were simply not there. This was the first thing detected, in effect, from inside the sun that should not have been possible. And it threw solar physics into genuine crisis. Because there were only two ways to explain it, and both were deeply uncomfortable. Either our model of the sun's core was badly wrong, meaning the fusion at the center was running much cooler or slower than we thought, and our supposedly perfect understanding of the sun was an illusion. Or our understanding of the neutrinos themselves, our understanding of fundamental particle physics, was missing something crucial. Either the sun was not what we thought, or physics was not what we thought. Neither was an easy thing to accept. This puzzle became known as the solar neutrino problem, and it persisted for decades. It was not a small discrepancy that could be waved away. Two-thirds of the expected neutrinos were missing, a vast, glaring shortfall confirmed again and again as detectors improved. Scientists checked everything. They refined the solar models. They rebuilt the detectors. They scrutinized the calculations of how many neutrinos the core should produce. And still, the neutrinos kept coming up short. Something somewhere was profoundly wrong, and for a long time no one could say what. It is worth sitting with how serious this was, because it sets the pattern for everything that follows tonight. Here was a case where we pointed our instruments at the inside of the sun and got an answer that flatly contradicted our best, most trusted understanding. The temptation in such a moment is to assume the measurement is faulty or that some boring error is to blame. But the discrepancy was real. And the resolution, when it finally came, did not just patch a hole in our knowledge. It revealed something genuinely new about the universe, something no one had known before. The missing neutrinos were trying to tell us a secret, and it took decades to understand what it was. That resolution is one of the most beautiful stories in modern physics, and it teaches us exactly how to think about the even deeper mystery still hiding inside the sun today. The solution to the solar neutrino problem, when it finally arrived, was one of the most beautiful twists in the history of physics, and it turned out that the sun was not the thing that was wrong. The neutrinos were. Here is what had been missed. For a long time, physicists assumed that there was essentially one kind of neutrino coming from the sun, the type produced by fusion in the core, and that this type stayed the same on its journey to Earth. The detectors were built to catch that one type, but it turned out that neutrinos are stranger than anyone realized. There are actually 3 different types or flavors of neutrino, and astonishingly, a neutrino can change from one flavor into another as it travels through space. It can set out from the sun as one type and arrive at Earth as a different type entirely. Physicists call this neutrino oscillation. This was the key that unlocked everything. The sun's core was producing exactly the number of neutrinos the model predicted. The model was right all along. But on the 8-minute journey from the sun to the Earth, about 2/3 of those neutrinos quietly changed flavor into types that the early detectors simply could not see. The neutrinos were never missing. They were hiding in plain sight, transformed into a form the experiments were blind to. When scientists finally built a detector capable of sensing all 3 flavors at once, they found that the total number of neutrinos arriving from the sun matched the prediction almost perfectly. The shortfall vanished. The sun was vindicated. But notice what this resolution actually was. It did not just fix a bookkeeping error. The discovery that neutrinos can change flavor meant that neutrinos must have a tiny amount of mass, something that the existing theory of particle physics had not accounted for. In other words, the missing solar neutrinos had revealed a genuine gap in our understanding of fundamental physics itself. The strange behavior of these ghostly particles from the sun's core forced physicists to expand their theory of how the universe works at the most basic level. It was so important that it was eventually recognized with a Nobel Prize. And this is the lesson to carry with you for the rest of tonight. When we point our instruments at the inside of the sun and the answer comes back wrong, when something seems impossible, there are 2 possibilities. Sometimes it means our model of the sun is flawed. But sometimes it means we have stumbled onto something genuinely new about the universe, something the sun is uniquely positioned to reveal. The neutrino problem turned out to be the second kind. A puzzle that looked like an error but was actually a doorway into new physics. So when we come to the mystery that still haunts solar physics today, the one that has not yet been solved, keep that doorway in mind. Because for now, though, the resolution of the neutrino problem did something else. It made scientists more confident than ever that they truly understood the sun. And that confidence was about to be shattered. By the early years of this century, solar physics was riding high. The two great windows into the sun's interior had both delivered spectacular confirmations of the standard solar model, and scientists had every reason to believe they had finally, completely understood our star. Think about everything that was lining up. Heliosismology, the study of the sun's sound waves, had mapped the interior in exquisite detail, and the measured structure matched the model's predictions to a fraction of a percent. The depth of the convective zone, the speed of sound throughout the interior, the amount of helium, all of it agreed. And the solar neutrino problem, which had nagged at the field for decades, had been triumphantly resolved, with the discovery that the sun's core was producing exactly the neutrinos it should. Two completely independent methods, one probing the structure of the layers, the other probing the fusion in the core, both confirming the same detailed model. It was a stunning convergence. This was, by any measure, one of the great achievements of modern astrophysics. We had taken an object we could never touch, never enter, never directly see inside of, and we had built a mathematical model of its hidden interior so accurate that it survived test after independent test. The standard solar model became a cornerstone, not just of our understanding of the sun, but of our understanding of all stars. Because remember, the sun is the benchmark. If we understood the sun this well, then we could trust our models of every other star in the universe, all of which are built on the same physics. The sun was the foundation that the entire edifice of stellar astrophysics rested upon, and that foundation appeared rock solid. Scientists wrote, with justified pride, that the agreement between solar models and the measured interior was a triumph. The sun was held up as a shining example of how powerful physics could be, how we could understand even the most inaccessible places in the cosmos through careful reasoning and clever observation. There was a sense that this particular chapter was essentially finished. The interior of the sun was known. The model worked. What more was there to do but refine the details? And that is precisely the kind of confidence that the universe loves to humble. Because the entire towering structure of agreement rested on one quiet assumption, an assumption so basic that almost no one thought to question it. It rested on knowing exactly what the sun is made of, the precise recipe of chemical elements, the amount of carbon, of nitrogen, of oxygen woven into the sun. Everyone assumed those numbers were well established. They were not. And when scientists went back and measured them again, more carefully than ever before, the numbers changed. And the moment they changed, the beautiful agreement, the triumph, the rock-solid foundation, all of it came crashing down. The thing that shattered our perfect understanding of the sun was not a dramatic new discovery from a distant telescope. It was something far quieter, and in a way far more unsettling. It was a more careful measurement of something we thought we already knew. The chemical composition of the sun. Specifically, how much carbon, nitrogen, and oxygen it contains. Here is how scientists figure out what the sun is made of. When you split the sun's light into a spectrum, into all its component colors, you find it is crossed by countless dark lines. Each of those lines is a fingerprint, left by a specific chemical element in the sun's outer layers absorbing light at a particular wavelength. By measuring the darkness and position of those lines, scientists can work out how much of each element the sun contains. It is a powerful technique, and it had been used for decades to establish the sun's recipe, the precise proportions of hydrogen, helium, and the heavier elements like carbon, nitrogen, and oxygen. But turning those spectral lines into precise abundances requires a model of the sun's surface, a model of how the light is produced and absorbed in that churning, boiling outer layer. And in the early 2000s, scientists developed far more sophisticated models of the solar surface, accounting in much greater detail for the three-dimensional, turbulent motion of the plasma and for subtle effects in how the atoms absorb light. These new models were widely regarded as more realistic, more accurate, a genuine improvement over what had come before. And when scientists used them to remeasure the sun's composition, they got a different answer. The new measurements found that the sun contains noticeably less carbon, nitrogen, and oxygen than previously believed. The amounts of these key heavy elements came down by something like a quarter to a third. Now, on the face of it, this sounds like a small, technical adjustment. So the sun has a bit less oxygen than we thought. Who could possibly care? It seems like the kind of minor refinement that would barely make a ripple. The total amount of these heavy elements is tiny compared to the hydrogen and helium that make up almost all of the sun. How could shaving a quarter off such a small ingredient matter at all? It mattered enormously, because those heavy elements, carbon, nitrogen, oxygen, and a few others, play a role inside the sun that is wildly out of proportion to their tiny quantity. They are one of the main things that control how energy flows through the sun's interior. Change their amount, even by a little, and you change the entire internal structure of the star. And so when scientists took this new, more accurate composition and fed it back into the standard solar model to recalculate the interior, the model stopped matching the sun. The beautiful agreement, the triumph that had stood for years, simply collapsed. To understand why, we have to follow a single photon on its tortured journey out of the core. Let's be precise about what broke, because this is the heart of the entire mystery. When scientists rebuilt the standard solar model using the new, lower amounts of carbon, nitrogen, and oxygen, the model began to disagree with the real, measured interior of the sun in several specific, glaring ways. And these were not the kind of small discrepancies you could shrug off. They were far larger than any reasonable uncertainty in either the measurements or the model. Remember that crucial boundary deep inside the sun, the depth where the radiative zone ends and the churning convective zone begins. Heliosysmology, by listening to the sun's sound waves, had measured exactly where that boundary sits with great precision. The old solar model with the old composition had predicted that boundary in exactly the right place. But the new model with the revised composition predicted it in the wrong place. It put the boundary too shallow, too close to the surface, disagreeing with what the sound waves clearly showed. The model and the real sun no longer agreed on the basic architecture of the interior. And it was not just that one boundary. The new model also got the speed of sound wrong throughout parts of the interior, deviating from the precisely measured profile that heliosysmology had established. It predicted the wrong density in certain layers, and it got the amount of helium in the sun's outer regions wrong, again disagreeing with the heliosysmic measurements. Across multiple independent checks, the model built with the more accurate composition failed to match the actual, measured inside of the sun. The two pictures, the predicted interior and the observed interior, had come apart. It was genuinely strange here. We now had a contradiction baked into the very heart of our understanding. On one side, we had what appeared to be a more accurate measurement of what the sun is made of, using better, more realistic models of its surface. On the other side, we had direct, precise measurements of the sun's actual interior structure, from sound waves and other methods that we also trusted deeply. And these two things could not both be right. The composition we measured at the surface predicted an interior that simply was not the interior we observed. Something, somewhere, in our understanding of our own star was wrong, and it was not at all obvious what. This is what scientists came to call the solar abundance problem, or sometimes the solar modeling problem. And it is not some obscure historical footnote. It remains, right now, an active and unresolved puzzle in solar physics. We literally cannot make the inside of the sun add up. We cannot simultaneously match the composition we measure at its surface and the structure we measure in its interior. One of our most basic, trusted pieces of knowledge about the closest star to us is broken, and despite years of intense effort by brilliant people, no one has been able to fully fix it. To understand why it is so stubborn, you have to understand the strange and crucial role those heavy elements play in the dark, slow journey of energy through the sun. To understand why a tiny change in the sun's composition could wreck our model of its entire interior, we need to follow the energy on its journey out of the core. And it is one of the strangest journeys in nature, a journey that depends, surprisingly, almost entirely on those trace heavy elements we just talked about. Energy is made in the core, in the form of light, as photons born from fusion. To escape, that energy has to travel outward through the radiative zone, the dense layer wrapped around the core. And as we touched on earlier, it does not travel in a straight line. The interior is so packed with matter that a photon can only fly a tiny distance before it crashes into a particle, gets absorbed, and is then re-emitted in a completely random direction. So the energy does not stream outward. It staggers, bouncing in a chaotic, drunken walk, taking an immense span of time, tens of thousands of years, to work its way through this single zone toward the surface. Now here is the crucial question. How easily can light push its way through this dense interior? How often does it get absorbed and re-emitted, and how much does that slow it down? Scientists have a word for this resistance to the flow of radiation. They call it opacity. A region with high opacity is hard for light to pass through, absorbing it readily. A region with low opacity lets light flow more freely. And the opacity of the sun's interior is what controls the temperature structure, how the heat is distributed at every depth, and ultimately where that all-important boundary between the radiative and convective zones ends up sitting. So what determines the opacity? This is the key to the whole mystery. The hydrogen and helium that make up almost all of the sun are deep in the hot interior, stripped bare and relatively transparent to radiation. They do not block light very effectively. It is the heavier elements, carbon, nitrogen, oxygen, neon, iron, that do most of the work of absorbing radiation in the interior. Even though they are present in tiny amounts, these heavy elements are responsible for a large share of the sun's internal opacity. They are the things that make it hard for light to escape, and in doing so, they shape the entire internal structure of the star. Now you can see why a small change in their abundance is so catastrophic for the model. If you reduce the amount of carbon, nitrogen, and oxygen, you reduce the opacity of the interior. Light flows more easily. The temperature structure shifts, and the boundary between the radiative and convective zones moves to the wrong place, no longer matching what the sound waves tell us. The trace heavy elements, despite their tiny quantity, hold the entire internal structure of the sun in a delicate balance, and the revised, lower abundances knock that balance out of alignment. So the problem is real, and it is deep. And that has sent scientists scrambling for a way to fix it, hunting for the one piece of the puzzle that could bring the sun back into agreement with itself. Faced with a contradiction at the heart of our closest star, scientists did what scientists do. They went hunting for the missing piece, the one adjustment that could reconcile the sun's measured composition with its measured interior. And over the years, several promising ideas have been chased down. But here is the remarkable thing. None of them has fully solved the problem. Every door they have opened has led, so far, to another wall. The first and most natural suspect was the opacity itself. Remember, the opacity, the resistance of the interior to the flow of radiation, is what got thrown out of balance by the new composition. So scientists wondered, what if our calculations of the opacity are simply wrong? What if the real opacity of the sun's interior is higher than our theories predict? A higher opacity could compensate for the reduced heavy elements and push the internal structure back into agreement with the measurements. This was a genuinely exciting possibility, and it was put to the test in a remarkable experiment, where scientists recreated the extreme conditions of the sun's interior in a laboratory and measured the opacity of iron under those conditions directly. And intriguingly, they found the opacity was indeed higher than the models predicted. This was a real clue. But when the numbers were worked through, the effect, while real, did not appear to be large enough to fully close the gap on its own. Another idea focused on a specific element, neon. Neon is one of the heavy elements that contributes to the interior opacity, but its abundance in the sun is notoriously difficult to measure because, unlike many elements, it does not leave clear fingerprints in the part of the sun's spectrum we can easily study. So scientists wondered, what if the sun actually contains more neon than we think? Extra neon would raise the opacity and could help restore the agreement. Some measurements, looking at neon in other stars similar to the sun, hinted that the solar neon abundance might indeed be higher than assumed. It was another promising lead. But again, on its own, it did not seem to be quite enough to fully resolve the discrepancy. Still other ideas have been explored. Perhaps there is some additional mixing of material inside the sun that the standard model leaves out. Perhaps the revised composition measurements themselves are not the final word, and the true abundances lie somewhere between the old and new values, a debate that genuinely continues among experts to this day. Each of these ideas captures part of the puzzle. But the frustrating, fascinating reality is that, even now, no single explanation has cleanly and completely reconciled the sun's surface composition with its interior structure. The solar abundance problem stubbornly persists, and that persistence has pushed some scientists toward a far more radical possibility. What if the reason we cannot make the inside of the sun add up is that there is something inside the sun we have not accounted for at all? Something invisible. When every conventional fix fails to fully solve a problem, scientists are sometimes forced to consider explanations that sound, at first, like science fiction. And in the case of the solar abundance problem, one of the most intriguing ideas on the table involves the most mysterious substance in the entire universe: dark matter. The radical proposal is this: perhaps the reason we cannot make the inside of the sun add up is that there is dark matter hiding in its core. To understand this idea, you first have to understand what dark matter is, or rather, how little we know about it. Across the universe, astronomers have found overwhelming evidence that there is far more matter than we can see. Galaxies spin too fast to be held together by the gravity of their visible stars alone. The gravity of galaxy clusters bends light far more strongly than their visible matter could explain. Everywhere we look, there is the gravitational pull of something invisible, something that gives off no light at all. We call it dark matter, and it appears to make up the vast majority of all the matter in the universe, far more than all the stars and planets and gas combined. And yet, despite decades of searching, no one has ever directly identified what it is. It remains the single largest mystery in all of physics. Now here is the connection to the Sun. Dark matter is not just out in distant galaxies. If it is real, and the evidence strongly suggests it is, then it should be everywhere, including right here, drifting through our own solar system. Our Sun, as it orbits the center of the galaxy, is constantly moving through a sea of this invisible material. And some physicists have proposed that, over the vast lifetime of the Sun, some of that dark matter could become trapped inside it, captured by the Sun's enormous gravity, slowly sinking down and accumulating in the core. If that is true, then the heart of our star would contain a hidden component, a population of invisible particles that our standard solar model knows nothing about. And crucially, that hidden dark matter could affect the Sun's interior in just the right way to help solve our mystery. Because if dark matter particles are gathered in the core, they could potentially carry heat around in a way that ordinary matter does not, subtly altering the temperature structure deep inside the Sun. And altering that temperature structure could, in principle, shift the interior back toward what heliosismology actually measures, helping to close the very gap that has stumped scientists for years. It is a genuinely tantalizing idea. The thought that the invisible matter that dominates the entire cosmos might be pooling, unseen, in the center of our own Sun, secretly reshaping its core, and that this could be the key to a stubborn solar mystery. Now, it is essential to be honest here. This is a speculative idea, not an established fact. It is a minority hypothesis, a long shot, and most scientists do not believe it is the most likely solution to the abundance problem. But it has not been ruled out, and it remains a real, active area of investigation. And the mechanism behind it, the way an invisible particle could quietly hide inside a star and change its inner workings, is worth understanding, because it reveals just how much room for the unknown still exists, even in the best studied object in the sky. So how, exactly, could dark matter end up trapped inside the Sun? The idea sounds absurd at first. The Sun is a roaring furnace of hot plasma. How could a particle from the dark, cold depths of the galaxy ever get captured and held inside it? The proposed mechanism is subtle and surprisingly elegant. Start with the fact that dark matter, whatever it is, barely interacts with ordinary matter. That is precisely why we cannot see it. It does not absorb or emit light, and for the most part, it passes straight through normal matter as if it were not there, much like the neutrinos we met earlier. So most dark matter particles drifting through the galaxy would pass right through the Sun and out the other side, completely unaffected. But not all of them. Every so often, by chance, a dark matter particle passing through the Sun might bump into one of the atomic nuclei inside it. In that rare collision, the dark matter particle would lose a little bit of its energy, slowing down slightly. And that tiny loss of speed can be decisive. If a dark matter particle slows down just enough while passing through the Sun, it can no longer escape the Sun's powerful gravity. It becomes gravitationally bound, trapped, doomed to orbit within the Sun. And over time, through further interactions, it would gradually sink down toward the center, drawn into the core. Now multiply this rare event by the staggering number of dark matter particles the Sun has swept up over billions of years, as it plowed through the galaxy's dark matter again and again, orbit after orbit. The proposal is that, slowly, patiently, a population of dark matter could build up in the Sun's core, an invisible reservoir gathered over the entire age of the star. And here is where it could affect the Sun's structure. Once these dark matter particles are gathered in the core, they could move around within it, traveling from the hottest central regions out to slightly cooler ones, and in doing so, carrying heat with them. In effect, the dark matter could act like an additional way of transporting heat through the core, smoothing out the temperature, making the very center slightly cooler, and the surrounding regions slightly warmer than they would otherwise be. And remarkably, that is roughly the kind of adjustment that some versions of the abundance problem seem to call for. A slightly altered temperature structure deep inside could nudge the predicted interior back toward the measured one. But, and this is a crucial but, this only works if dark matter has very particular properties, a specific mass, and a specific, tiny tendency to interact with ordinary matter. And those properties are tightly constrained by other experiments, the great underground detectors built specifically to hunt for dark matter directly. So far, those constraints make the simplest versions of this solar dark matter idea difficult to sustain. It is not impossible, but it is squeezed from many directions, which is why, for now, it remains a fascinating possibility rather than an answer. The Sun may be hiding dark matter in its heart, or it may not. We genuinely do not yet know. And while that exotic question hangs unresolved, the Sun keeps presenting us with other behaviors that defy our understanding, like an atmosphere that breaks one of the most basic rules of physics. While scientists wrestle with the mystery buried in the Sun's core, there is another, completely separate puzzle playing out just above its surface, in the Sun's atmosphere. And it is one of the most stubborn and counterintuitive problems in all of solar physics. It is so strange that it seems to violate one of the most basic rules we know about heat. Here is the rule. Heat flows from hot things to cold things, and as you move away from a source of heat, you get cooler. Stand near a fire and you feel its warmth. Step back and the warmth fades. This is one of the most fundamental and intuitive facts about the physical world. Now apply it to the Sun. The energy is generated in the core and flows outward to the surface. So the surface, which we have said sits at around 5,500 degrees, should be the last warm thing before the cold of space. As you move out into the Sun's thin outer atmosphere, away from all that heat, the temperature should drop. It does the opposite. The Sun's outer atmosphere, called the corona, the faint halo you can see during a total solar eclipse, is not cooler than the surface. It is dramatically, impossibly hotter. The corona reaches temperatures of 1 to 3 million degrees, hundreds of times hotter than the surface just below it. It is as if you walked away from a campfire into the night, and instead of getting colder, the air around you became hot enough to melt metal. The heat appears to be flowing the wrong way, from the cooler surface out into the much hotter atmosphere, in apparent defiance of the basic rule that heat flows from hot to cold. This is called the coronal heating problem, and it has puzzled scientists for the better part of a century. Something is dumping enormous amounts of energy into the Sun's outer atmosphere, heating it far beyond the surface temperature, and for a long time, no one could say exactly what. It is another case, like the ones we have been exploring, where we look closely at our own star and find behavior that our models struggle to explain. The Sun, it seems, is full of these surprises. Scientists do have leading suspects. One idea is that the Sun's tangled, snapping magnetic field is constantly releasing countless tiny bursts of energy in the corona, far too small to see individually, but together enough to heat it to millions of degrees. Another is that waves of energy travel up from below along the magnetic field lines and deposit their energy high in the atmosphere. The truth likely involves some combination, and recent missions flying closer to the Sun than ever before are gathering crucial new data. But the fact that this remains an open question for the closest star to us is humbling. We cannot yet fully explain why the Sun's own atmosphere is hundreds of times hotter than its surface. And the deeper we look, the more the Sun seems to keep its secrets, including, perhaps, a secret about how its very heart is spinning. We have talked about how heliosismology, the study of the Sun's sound waves, lets us map the interior. But there is a limit to what those sound waves can tell us, and it concerns the deepest, most hidden part of the Sun, the core, and what little we have managed to learn about how the core spins hints at yet another surprise. Here is the limitation. The sound waves that heliosismologists usually study, the ordinary pressure waves rippling through the Sun, are excellent at mapping the outer and middle regions of the interior. But they do not penetrate cleanly into the very deepest core. They spend most of their time in the outer layers, so they tell us a great deal about those regions, but the heart of the Sun remains stubbornly veiled even to them. To truly probe the core, scientists would need a different kind of wave, a type called a gravity wave, which would travel through and resonate within the deep interior. The trouble is that these gravity waves, if they exist in the Sun, are trapped deep inside and barely reach the surface at all, making them extraordinarily difficult to detect. For decades, finding them was considered one of the great challenges of solar physics, a kind of holy grail. Then, a few years ago, a team of scientists made a startling claim. After analyzing many years of data on the Sun's vibrations, they reported that they had finally found the subtle fingerprint of these elusive gravity waves, and therefore a window into the core. And what their analysis suggested was remarkable. It indicated that the Sun's core is rotating much faster than its outer layers. Not a little faster, around 4 times faster. The heart of the Sun, by this result, would be spinning far more rapidly than the surface we see, a hidden, fast-whirling core buried inside the more slowly turning body of the star. If true, this would be genuinely fascinating, and it would make a certain kind of sense. When the Sun first formed from a collapsing cloud, it likely spun much faster than it does today. Over billions of years, the outer layers have been gradually slowed down, braked by the Sun's magnetic field interacting with the solar wind streaming out into space. But the deep core, more isolated, might have held onto more of that original rapid spin, like a hidden flywheel still turning fast at the center while the outer shell winds down. A fast core would be a kind of fossil, a memory of the Sun's swift youth, preserved deep inside. But here, once again, honesty is essential. This claim of a rapidly spinning core is intriguing, but it is not settled. The detection of these deep gravity waves is genuinely difficult and remains disputed. Other scientists have questioned whether the signal is really there, or whether it could be an artifact of the analysis. So this is not an established fact, but a tantalizing, contested hint, one more place where our knowledge of the Sun's deep interior becomes uncertain and strange. Whether or not the core truly spins that fast, the very fact that we cannot easily settle the question shows how much remains hidden. And nowhere is that hidden complexity greater than in the part of the Sun responsible for its magnetism, an engine we still cannot fully explain. The Sun is not just a ball of hot gas. It is a magnetic object wrapped in powerful, ever-changing magnetic fields. These fields are responsible for sunspots, for solar flares, for the great eruptions that can reach across space and disrupt life on Earth. And they are generated deep inside the Sun, by a process that, despite all our study, we still do not fully understand. The sun's magnetic engine is one of the most important mysteries hidden within it. The process that generates the sun's magnetism is called a dynamo. The basic idea is that the sun's interior is made of plasma, which is electrically charged, and as this charged material churns, flows, and rotates, it can generate and amplify magnetic fields. The motion of the plasma creates magnetism, and that magnetism in turn shapes the motion in a complex, self-sustaining cycle. This is, in broad strokes, how the sun is thought to produce its magnetic field. But the details, the precise way it all works, remain genuinely murky. A key piece of the puzzle is thought to lie in that thin transition layer we mentioned earlier, the tachocline, which sits at the boundary between the deep radiative zone and the churning convective zone. Below the tachocline, the sun rotates roughly as a solid body, all at the same rate. Above it, in the convective zone, different latitudes rotate at different speeds, with the equator spinning faster than the poles. The tachocline is the place where these two different patterns of rotation meet and grind against each other, a layer of intense shearing. And many scientists believe this shearing layer is where the sun's magnetic field is largely organized and generated, the very seat of the solar dynamo. It is a crucial, hidden region, deep inside the sun, that we cannot observe directly and can only probe indirectly. The trouble is that no one has been able to build a complete, fully successful model of the solar dynamo. We can capture parts of it. We can reproduce some of the sun's magnetic behavior in computer simulations. But a full, predictive theory that explains all the features of the sun's magnetism, why the cycle behaves exactly as it does, how the field is generated in detail, has remained out of reach. The engine that drives the sun's magnetic life, hidden in the shadows of its interior, is still not something we truly understand. And this is not a trivial gap. The sun's magnetic field shapes everything about its violent, active behavior, the behavior that directly affects us here on Earth. The fact that we cannot fully model the engine that produces it means we cannot fully predict it either. We are in the strange position of living beside a powerful magnetic star, whose inner workings we have only partly deciphered. And nowhere does that incomplete understanding show itself more clearly than in our repeated failure to predict one of the sun's most basic rhythms. Its 11-year cycle. If we truly understood the engine inside the sun, the dynamo that generates its magnetism, then we should be able to predict its behavior. And the most obvious thing to predict would be the sun's great cycle, the rhythm of its activity that rises and falls roughly every 11 years. But here, too, the sun humbles us. Because despite knowing this cycle exists for a long time, we still cannot reliably predict it. The cycle itself is well known. Roughly every 11 years, the sun swings from a quiet period, with few sunspots and little activity, up to a stormy peak, covered in sunspots and frequently erupting with flares, and then back down to quiet again. Underlying this is an even longer pattern, in which the sun's entire magnetic field flips its direction at the peak of each cycle, so that the full magnetic cycle is actually about 22 years. This much we have observed and documented. The rhythm is real, and it is one of the most fundamental features of our star's behavior. But knowing that the cycle exists is very different from being able to predict its details. And those details matter enormously, because the strength of each cycle determines how much dangerous space whether the sun will throw at us over the coming years. Will the next peak be intense, with many powerful storms, or will it be mild and quiet? How strong, exactly, will the activity become, and precisely when will it peak? These are the questions we desperately want to answer, and our track record at answering them is poor. Scientists make predictions for the strength of each upcoming cycle, and those predictions frequently disagree with one another and frequently turn out to be wrong. In fact, the cycle we are living through right now has been a pointed reminder of our ignorance. Many forecasts predicted it would be relatively weak. Instead, the sun has been considerably more active than those predictions suggested, producing more sunspots and more powerful storms than expected. The sun, once again, did not behave the way our models said it should. It outran our forecasts, and the reason we cannot predict the cycle reliably is precisely that we do not fully understand the dynamo that drives it, the magnetic engine hidden deep in the interior. So here is the picture that emerges. We cannot fully model the sun's magnetic engine. We cannot reliably predict its cycle. We cannot cleanly account for the structure of its interior. We have an unconfirmed hint that its core may spin far too fast. We cannot fully explain why its atmosphere is hundreds of times hotter than its surface. And we have a deep, unresolved contradiction between its measured composition and its measured interior. The sun, the star we once declared essentially solved, turns out to be riddled with open questions. And sometimes, the sun reminds us of its hidden power in the most dramatic way possible, by literally shaking, sending quakes rippling across its surface. For all the subtle, hidden mysteries inside the sun, every so often it does something violent and visible that reveals just how dynamic its interior truly is. The sun can experience earthquakes, or more precisely, sunquakes, and they are one of the most dramatic phenomena ever observed on our star. Here is what happens. When the sun unleashes a particularly powerful solar flare, a sudden, enormous release of magnetic energy at the surface, the impact can send a shockwave plunging down into the sun and rippling outward through its interior and across its surface. The result is a seismic wave, a literal quake in the body of the sun, much like an earthquake here on Earth, but on a scale that defies belief. Scientists first clearly observed this in the late 20th century, watching in astonishment as ripples spread outward across the sun's surface from the site of a major flare. And these are not gentle ripples. A sunquake spreads out in expanding circular waves, like the ripples you get when you drop a stone into a pond, but the scale is staggering. The waves race outward across the sun's surface at enormous speeds, and they can travel across distances many times the size of the entire Earth. The energy released in a single large sunquake can rival or exceed the energy of the most powerful earthquakes our planet has ever experienced, by a vast margin. To watch a sunquake unfold is to see the entire surface of the sun shudder and ring from a single violent event, the disturbance racing outward in beautiful, expanding rings. And beyond their sheer drama, sunquakes are scientifically valuable because they give scientists yet another way to probe the interior. Just as the sun's constant, gentle ringing allows heliosseismologists to map its structure, these sudden, violent quakes send waves plunging through the interior that carry information about the layers they pass through. By studying how a sunquake's waves travel and spread, scientists can learn more about the conditions beneath the surface, adding another tool to the small set of methods we have for seeing inside our star. But sunquakes also underline a deeper point. They reveal just how violently the surface of the sun is coupled to the turbulent layers beneath it, how a single eruption can set the whole star ringing. The sun is not a calm, static object whose interior sits quietly beneath a placid surface. It is a churning, shaking, magnetically violent body, full of motion and energy we are still struggling to fully comprehend. And to understand it better, to finally crack some of these stubborn mysteries, scientists have done something that would have seemed like pure fantasy not long ago. They have sent a spacecraft to fly directly into the sun. For all of human history, the sun was utterly untouchable, a thing to be observed only from an enormous distance. The idea of sending a machine to the sun, of actually flying into it, would have sounded like madness or pure fantasy. And yet, that is exactly what we have done. We built a spacecraft and sent it to fly directly into the outer atmosphere of the sun, to touch our star. The spacecraft was launched several years ago on an audacious mission, to fly closer to the sun than anything ever built, plunging again and again through the sun's blazing corona to study it from within. To survive, it was fitted with a revolutionary heat shield, designed to withstand temperatures of thousands of degrees, while keeping its instruments safe and cool just behind it. And it was sent on a series of looping orbits that carry it ever closer to the sun, using the gravity of the planet Venus to tighten its path, edging nearer and nearer to the surface with each pass. And it has achieved something extraordinary. The spacecraft has flown directly through the sun's corona, becoming the first human-made object to enter the atmosphere of our star and survive. It has swooped to within just a few million miles of the surface, closer than anything before it, into a region of searing heat and ferocious radiation. And in doing so, it became the fastest object humans have ever built, whipping around the sun at speeds of hundreds of thousands of miles per hour, flung along by the sun's immense gravity. To picture it is to picture a tiny, fragile craft, shielded against an inferno, racing through the outer fire of the sun and living to send its data home. And that data is directly aimed at some of the mysteries we have been exploring. By flying through the corona itself, the spacecraft can measure the conditions there directly, the magnetic fields, the flowing particles, the bursts of energy, gathering exactly the kind of information needed to finally crack the coronal heating problem, that stubborn puzzle of why the atmosphere is hundreds of times hotter than the surface. For the first time, instead of studying the corona from afar, we have an instrument inside it, taking its measurements on the spot. And it is already revealing surprises. Among its discoveries, the spacecraft found that the magnetic field in the solar wind, the stream of particles flowing out from the sun, is full of strange, sudden reversals, abrupt kinks where the magnetic field briefly flips back on itself before snapping forward again. These features were unexpected, and scientists are still working to understand exactly what causes them, and what they tell us about how the solar wind is born and how the corona is heated. Once again, when we look closely at the sun, we find behavior we did not predict. The mission continues, flying closer with each pass, and the hope is that, from inside the fire, it will help us answer questions that have resisted us for generations. But flying into the sun is not the only astonishing thing we can now do. We can also, in a sense, see straight through it, to the far side we are not even facing. Here is something that sounds genuinely impossible, and yet we can do it. We can see the far side of the sun, the side facing away from us, the half of the sun that is, at any given moment, turned completely away from the Earth and hidden from all our telescopes. We can detect what is happening over there, on a face of the sun we cannot directly look at, and it comes, once again, from the magic of listening to the sun's sound waves. The side turned toward us. The other half is hidden behind the enormous bulk of the star, and because the sun rotates, regions on the far side will eventually turn to face us, but until they do, they should be completely invisible. This matters because the sun's far side can host large, active regions, great clusters of magnetic activity that produce powerful storms. It would be enormously useful to know they are there before they rotate into view and potentially aim their eruptions at Earth. But how could you possibly see them, hidden as they are on the opposite face of the sun? The answer, remarkably, is heliosismology again. Remember that sound waves travel all the way through the body of the sun, passing through its interior and bouncing around inside it. That means the sound waves rippling on the side of the sun we can see have, in part, traveled through the entire sun, including the far side. And an active region on the far side subtly affects those sound waves as they pass through, leaving a faint imprint on the vibrations we can measure on the near side. By carefully analyzing the sound waves on the visible face of the sun, scientists can reconstruct what must be happening on the hidden far side, effectively creating a map of a part of the sun no telescope can directly observe. This is a genuinely astonishing capability. By listening to the ringing of the near side, we can detect large active regions lurking on the far side, days before they rotate around to face us. We are, in a real sense, seeing through the sun, using its own internal sound to image a face turned entirely away from us. It is one more example of how clever scientists have been in finding ways to probe a star we can never touch, wringing information about its hidden parts from the subtle vibrations of its surface. And it underscores the central theme of everything we have explored tonight. The inside of the sun, and even the hidden side of the sun, are not as unreachable as they first appear. Through sound waves, through neutrinos, through spacecraft flying into the corona, we have found ways to extract astonishing amounts of information from a place that should, by all rights, be sealed off from us. And yet, for all that ingenuity, for all these incredible tools, the deepest puzzle remains. We can map the interior in stunning detail, and still, the interior we measure does not match the interior our best models predict. We have looked and looked, and the contradiction stubbornly endures. And that endurance is not just a curiosity. It threatens something much bigger. It would be easy to think of the solar abundance problem as a narrow, technical issue, an obscure disagreement between specialists about the details of one particular star. But it is far more serious than that, and to understand why, you have to remember the unique role the sun plays in all of astronomy. The sun is not just one star among many. It is the foundation on which our understanding of all stars is built. And that is exactly what makes this unsolved problem so unsettling. Here is the situation. Every other star is so far away that we can never study it the way we study the sun. We cannot resolve its surface in detail, cannot map its interior with anything like the precision we have for our own star. So when scientists model other stars, when they try to understand how stars across the universe are born, how they live, how they age and die, they rely on the physics they worked out and tested on the sun. The sun is the calibration point, the one example we can check against reality in exquisite detail. If our model of the sun is correct, we can trust that the same physics, applied to other stars, is probably correct too. The sun is the benchmark that gives us confidence in everything else. So consider what it means that we cannot fully model the sun. If there is a genuine gap in our understanding of the closest, best studied star in existence, a star we can probe with sound waves and neutrinos and spacecraft, then what does that say about our models of all the other stars, which we can only observe as distant points of light? If we cannot make the inside of our own sun add up, how confident can we really be about the insides of stars billions of times further away? The solar abundance problem is not just a problem for solar physics. It is a crack in the foundation of stellar astrophysics as a whole. The benchmark, in a sense, has failed, and everything built upon it inherits a measure of doubt. This is why scientists take the problem so seriously, and why they have worked so hard to solve it. It is not about tidying up one loose end. It is about whether we truly understand stars at all. And the stakes have grown even higher in recent years, because we have begun to study the interiors of other stars directly, using the very same technique we use on the Sun. Just as the Sun rings with sound waves that reveal its interior, other stars vibrate too, and modern telescopes have become sensitive enough to detect those tiny vibrations in distant stars, a field called asteroseismology. We are now mapping the insides of thousands of other stars across the galaxy, using the same method, the same physics, that we calibrated on the Sun. But that entire enterprise rests on getting the Sun right. If our understanding of the Sun's interior contains a fundamental error, that error could propagate into our understanding of every star we study this way. So the unsolved puzzle in the heart of the Sun casts a long shadow, reaching out across the whole galaxy, touching our understanding of stars we will never visit. To resolve it, scientists are now faced with a stark choice between two very different kinds of answer. After everything we have explored, the contradiction inside the Sun comes down to two broad possibilities, two fundamentally different kinds of explanation. And which one turns out to be correct will shape the future of solar physics, and perhaps of physics itself. It is worth laying them out clearly, because they represent two very different ways the universe could be. The first possibility is, in a sense, the less dramatic one, though it is far from trivial. It is that the answer lies in some piece of conventional physics that we have not yet gotten quite right. Perhaps our calculations of the opacity, the way radiation flows through the interior, are still subtly off, and a better treatment will close the gap. Perhaps the true abundances of certain elements, like neon, are different from what we currently assume, and a more accurate measurement will restore the agreement. Perhaps there is some additional mixing or process inside the Sun that the standard model leaves out. In this scenario, there is no new physics, no exotic substance, just a refinement of the complex, ordinary physics we already know, eventually bringing the model and the measurements back into harmony. Most scientists suspect the answer lies somewhere in this direction, in the difficult but familiar details. The second possibility is far more profound. It is that the contradiction is pointing, as the solar neutrino problem once did, toward genuinely new physics. That the reason we cannot make the inside of the Sun add up is that there is something present or something happening that our current understanding of the universe does not include. The dark matter hiding in the core is one version of this, but there could be others, surprises we have not even thought of yet. In this scenario, the Sun is once again playing the role it played with the neutrinos, acting as a unique laboratory that reveals a gap in our fundamental understanding of nature, a doorway into new discoveries about how the universe works. And here is the crucial point. We do not yet know which of these it is. The honest answer, the one scientists themselves would give, is that the solar abundance problem remains genuinely unsolved. It might be resolved tomorrow by a clever new opacity calculation, quietly closing the gap with no fanfare. Or it might persist and deepen, eventually forcing us to accept that something stranger is going on inside our star. Both outcomes are live. Both are being actively pursued. The Sun is keeping its secret and refusing, for now, to tell us which kind of secret it is. This is, in truth, what makes the problem so exciting rather than merely frustrating. Because remember the lesson of the neutrinos. The last time the Sun stubbornly refused to match our models, the resolution was not boring at all. It revealed that neutrinos have mass, expanding our understanding of fundamental physics and earning a Nobel Prize. The Sun has a track record of turning its anomalies into doorways. So when we look at the unsolved puzzle in its interior today, we are not just looking at an error to be corrected. We may be looking at the next great discovery, waiting to be made. And to make it, scientists are building a new generation of instruments designed to probe the sun as never before. The mysteries inside the sun will not be solved by giving up. They will be solved, if they can be solved, by looking harder, with better instruments from new vantage points. And right now, we are entering a genuine golden age of solar observation, with a fleet of new tools designed to probe our star in ways that were impossible just a short while ago. The frontier is wide open, and the next clues are already being gathered. We have already met the spacecraft flying directly through the sun's corona, plunging closer with each orbit, gathering measurements from inside the fire. That mission continues, and with every pass it sends back new data from a region we could never reach before, slowly building a picture of how the corona is heated and how the solar wind is born. Each close approach is a fresh chance to catch the sun in the act, to measure the very processes that have puzzled us for so long. But that is only one of our new eyes on the sun. Another spacecraft has been sent on a path that carries it out of the flat plane in which the planets orbit, climbing high enough to look down on the sun's poles, regions we have never been able to see clearly from Earth. This matters enormously, because the sun's poles are thought to play a key role in its magnetic engine, the dynamo that drives the entire solar cycle. By finally getting a clear view of the poles, scientists hope to gather crucial clues about how the sun generates its magnetic field, one of the deepest of all the mysteries hidden inside it. For the first time, we are seeing parts of the sun that have always been hidden from us. And it is not just spacecraft. On the ground, scientists have built a new generation of solar telescope, the most powerful ever made, capable of resolving features on the sun's surface in breathtaking detail, picking out structures astonishingly small on the face of the star. With instruments like this, we can study the fine details of the sun's surface and magnetic field, watching the small-scale processes that may hold the keys to the coronal heating problem and the workings of the magnetic field. The level of detail now available is unlike anything in the history of solar physics. Together, these tools represent a coordinated assault on the sun's deepest secrets, from inside the corona, from above the poles, and from the ground in unprecedented detail, along with ever-improving measurements of neutrinos and ever more sophisticated analysis of the sun's sound waves. Each one chips away at the mystery from a different angle. And somewhere in the flood of data they are gathering, the answer may be waiting, the missing piece that finally makes the inside of the sun add up, or the first solid evidence that something genuinely new is hiding in our star. We are closer than we have ever been. And whichever way it turns out, one thing has already changed forever: our relationship with the star we thought we knew. Let's step back now and take in the full shape of what we have explored tonight. Because the journey we have taken from confident certainty to deep and unresolved mystery says something important, not just about the sun, but about knowledge itself, and about the strange position we occupy in the universe. We began with a star we believed we had essentially solved. We had measured it, modeled it, and confirmed those models with two independent and almost miraculous windows into its interior: sound waves and neutrinos. We had every reason to be proud, and we were. The sun stood as a triumph of human understanding, a demonstration that we could comprehend even the most inaccessible places in nature through reason and ingenuity. And then, with a single, more careful measurement of what the sun is made of, that certainty dissolved, and we found ourselves face to face with a contradiction we still cannot resolve, buried in the heart of the closest star to us. And along the way, we found that this was not the only mystery hiding in the sun. We found an atmosphere hundreds of times hotter than the surface, in apparent defiance of basic physics. We found an unconfirmed but tantalizing hint that the core may be spinning far faster than the surface. We found a magnetic engine we cannot fully model, and a cycle we cannot reliably predict. We found the possibility, however speculative, that the invisible dark matter of the cosmos might be pooling in the sun's core. Layer by layer, the star we thought we had solved revealed itself to be full of open questions, a place of genuine and active mystery. There is something humbling in this, and also something wonderful. It would be easy to feel discouraged, to think that if we cannot even understand our own sun, we have failed. But that is the wrong way to see it. The fact that we can detect these mysteries at all, that we can measure the inside of a star precisely enough to know that our models are slightly wrong, is itself a staggering achievement. You cannot find a discrepancy of a fraction of a percent inside the sun unless you understand the sun almost perfectly to begin with. The mystery exists because of how much we know, not how little. We have understood the sun well enough to find the exact places where our understanding breaks down, and those places are where the next discoveries live. This is how science actually works, not as a finished collection of facts, but as a living conversation with the universe, in which every answer reveals new questions, and every triumph contains the seed of the next mystery. The sun has been talking to us this whole time, through its light, through its sound, through its ghostly neutrinos, and it is still telling us things we do not yet understand. The conversation is not over. It may never be over, and that is not a failure of science. It is the very thing that keeps it alive. So the next time you step outside and you feel the warmth of sunlight on your skin, take a moment to consider what is really happening and how much of it we still cannot fully explain. That warmth has traveled 93 million miles to reach you. But long before that, it began as energy in the core of the sun, in a place we can never go, behind a wall of fire we can never cross. It crawled outward for an immense span of time through layers, whose exact structure does not match our finest models. It passed through a boundary that sits in a place our theories cannot quite account for. It was shaped by an interior that, by everything we thought we knew about what the sun is made of, should not look the way it does. And then, finally, it broke free of the surface, crossed the emptiness of space, and landed gently on you. We have done astonishing things to understand that light. We have listened to the sun ringing like a bell and mapped its hidden depths from the music. We have caught the ghostly particles streaming from its core and used them to weigh the fusion at its heart. We have sent a fragile machine to fly directly into its blazing atmosphere and live. We have even learned to see the side of the sun that faces away from us by reading the echoes of its own sound. By any measure, we understand the sun more deeply than any star in the universe. And still, it keeps its secret. Still, when we check the inside of the sun against our best understanding, something does not add up. There is a discrepancy in the heart of our star of effort by some of the most brilliant minds on Earth. Know yet whether it will turn out to be a quiet matter of physics we already know, or whether it is a doorway, like the missing neutrinos once were, into something genuinely new about the universe. The sun is not telling us. Not yet. There is something almost fitting about that. The sun is the source of nearly all the energy that has ever powered life on Earth. It is the reason you exist, the reason anything here exists. It has been shining in our sky since long before there were eyes to see it, and it will go on shining long after tonight. It is the most familiar object in all the heavens, the one constant presence above every human life that has ever been lived. And yet, even now, Even after all we have learned, it holds a mystery in its core that we cannot explain. The thing that gives us everything is still, in its deepest heart, partly unknown to us. Maybe that is exactly as it should be. Maybe the sun is meant to remain a little beyond our grasp, a reminder that the universe is always larger and stranger than our models of it, that there is always more to learn, even about the things we thought we knew best. The sun has humbled us before and turned that humbling into one of the great discoveries of physics. It may be about to do so again. And until it does, we can stand here in its warmth, small creatures on a small world, gazing up at a star we have studied for centuries, and feel that particular kind of wonder that comes only from knowing exactly how much we still do not know. The light on your face is older than you can imagine, and it has crossed an emptiness vaster than you can feel. It comes from a star we have measured and modeled and very nearly understood. Very nearly. And in that small, stubborn gap, in that sliver of the sun that still refuses to add up, lies one of the quiet, beautiful mysteries of our time, waiting patiently in the heart of the light for someone to finally understand it.